number one is going to be a DC question, and number two is going to be an AC question. Okay? So the first question that I'm going to ask is, I'm going to put in a very long pulse that's just a DC pulse. So this is my current as a function of time. And so I inject current into that axon. And the question I'm going to ask is, if I take my voltmeter and I sample right here with my voltmeter, I'll put V question mark. And then I move a little further off over here, V question mark. And I do it either way. It'll be true either direction. Question mark, so on. So I'm actually going to be moving in this direction, which we'll call X. So I put in a non-depolarizing current pulse. The question is what does V look like as a function of X? Okay, this is the first question. How does that membrane react to me artificially injecting current into a part of that membrane? Okay? Well, if we do the experiment, and just empirically, I do the experiment and I make multiple measurements. And so I measure here, and here, and here, and here. I can fill in these data points. Okay? And so it turns out that you get your maximum depolarization, the maximum voltage, delta V, right where the electrode is, and then it exponentially decreases as you go away. So this is an exponential decrease in delta V. As a matter of fact, as an electrical engineer, I can come in and I can write an equation that actually describes that change in voltage. And so basically it's going to be delta V e to the minus some x or d over lambda. Lambda is what we call the spatial decay constant. And so this lambda, spatial decay, DC spatial decay constant, describes how that voltage decreases away from where I stimulate. Now, if you go back and you think of your electrical engineering background, what does that really look like? What kind of circuit element or elements would mimic that kind of a, empirically I've measured it, and it's an exponential decrease away from the point that I perturb the membrane. And so what kind of a element looks like that?
Capacitor.
Nope.
No.
No, there's no C's in this. What does a capacitor look like? What's the impedance of the capacitor, DC? What does a capacitor look like in DC? If I do a DC analysis, all the capacitors go away because the impedance is zero at DC. All right? Capacitors are open circuits at DC. They go away. You don't have to even have a capacitor. This is a DC test. No capacitor.
RL?
That's not an RL. RL is a second order. If I have an RL, I get something that looks like this. I'd have some kind of a, like that. So the only thing that I know of that produces this is a transmission line. And so basically you have, if I measure the voltage here, 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 dot, 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 down to here, okay, that voltage is going to do like this. Okay. So this looks like a transmission line. Okay? And so the way, again, that we kind of model this, we know that inside here, so here's the axon, okay? Inside here, there's some kind of R axon, And across here, there's another resistor here, which is called R membrane. And so this is R axon, and this is R membrane. And so as I sample from here to here, I'm getting an exponential decay that depends upon those values of axoplasmic resistance and membrane resistance. And from a mathematical standpoint, I can become more formal and say that the spatial decay constant, again, not justifying it, but empirically it's going to be the square root of the membrane resistivity, membrane resistance divided by the axoplasmic resistance. That comes directly from the transmission line decay model. Okay? Now note here that this is all a DC analysis. There's no action potentials. All I've done is a subthreshold, just probe the properties of that membrane. Okay? Any questions about that? Like perfectly confused, right? No.
What do you mean by exoplasmic resistance?
Okay.
Explain that.
Yeah, actually we're gonna actually calculate what that is. Okay, inside the neuron, there's a goo, right? It's called cytoplasm, right? And that has a resistance. Okay, I can put a number on it. Remember that resistance is equal to rho L over A, where this is A and this is L. And rho is the intrinsic resistivity of the goo that's inside that neuron. Does that answer your question?
Yeah.
Probably not. Okay. Any other questions? Now we're going to do experiment number 2. So we're going to forget this one, and now we're going to do the AC analysis. So we're going to still have our same setup here, except now we're going to do the AC analysis. Okay. And so what I do now is I ask a different question. I'm going to put in now a very short pulse, something that looks like this. I'm going to put in something that looks like an AC pulse this time. And so this is going to be my I here as a function of time. And this is time on that scale here. So instead of checking different places here, I'm just going to put my voltmeter in one place. So actually I've made it a little bit easier. And so the question is, if I put in a sharp pulse, what does the voltage look like? And so here's my input. Like this. This is I, and what does my V look like? There's the question. So it's a different problem I'm asking it. I'm not looking at different places as I go down the membrane. I'm just asking, the question I'm asking is, what does the AC response of the membrane look like to the unit step function? Okay? Well, when I do the test, and I put that short pulse in, guess what? So the voltage that I measure goes up like this, and then it exponentially decays like that. So exponentially up and exponentially down. So this is a different test, and this is now not a function of x, but it's a function of t. Okay, so, yeah.
So the second pulse is not in effect. Does it cause it to go back up?
Yeah, it keeps going up and down, up and down. I mean, this is this goes on indefinitely if I keep stimulating it with an AC pulse train. Just keep repeating. I just showed the first couple of cycles. Okay. And so I ask you again, you electrical engineers, how do you model this phenomenon? What does that remind you of? Where up and down. Hey, it looks like I'm charging a capacitor, so it looks like this. It looks like, here's my source here, and I have some kind of a resistance, and I have a capacity. And this is the voltage that I'm measuring. And, you know, if you're not convinced, this is actually the kind of the analysis. So, if you do, so a unit step, and if you do the Laplace transform of a unit step, it's 1 over S, and R is R, and the impedance of the capacitor is 1 over SC. And so if you do the little voltage divider equation, okay, turns out that in a closed loop form, you can solve it. And so you end up with this exponential with a time constant. So you do this has a time constant. And that time constant is 1 over RC. So the bottom line is that our membrane looks like a transmission line, but it also looks like a resistance and a capacitance. Now, how do you put that all together? We've done our experiment, and we know that it kind of looks like this. So the way that we kind of put this all together is with a thing that's called the Hodgkin-Huxley model of the neuron. And so here we have axoplasmic resistance, membrane resistance. So these two determine the lambda decay constant. And we also have this membrane capacitance. And the membrane capacitance is what determines its AC properties. So if I were to go down the neuron, here, 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 I'm going to get an exponential decay by putting a DC value, DC perturbance here. But if I also ask the other question, if I put in a pulse train here, I'll see that exponential rise and fall because of this capacitor and this resistance. So what I've done here is to take our experiment and combine our experimental results to come up with a model that we can use to calculate how fast this signal that we're putting in is going to propagate and perturb that membrane. Now, I want to also point out, so you're perfectly clear, we have not said one single thing about an action potential. These are passive membrane properties. Passive membrane properties. Passive. These are passive membrane properties. And we can absolutely put numbers on all these things. You all have enough for today, or do you want to do a little more math? Okay. This is actually a pretty good break here, but when we come back the next time, I'm going to show you how you calculate axoplasmic resistance, membrane resistance, and membrane